the European Synchrotron Radiation Facility. He's speaking to us today from France. So Marius earned his PhD from the Joseph Fourier University in Molecular and Structural Physical Chemistry. He did a postdoc at Max Planck Institute in Chemical Energy Conversion in Germany, followed by a permanent appointment at the ESRF, where he developed CRISPy, a Python-based program for X-ray spectroscopy calculations. Today, Marius will tell us why we all need to use the NeXus data format. So with that, thank you.
Yeah, thank you. Thank you for the introduction, Shelley, and thank you for having me today. So this presentation is based on a small demo that I gave about 2 months ago at one of the group meetings where we are trying to establish a new NeXus definition for X-ray absorption spectroscopy. But since that demonstration was based on the assumption that everybody was familiar with HDF5, which maybe is not the case here, I want to start a little bit by introducing some of the formats that are, let's say, used in X-ray spectroscopy and a few details about it. So as spectroscopists, we love plain text files, and most of the times, if you have a file with 2 columns, that's good enough for us. If you want to go one step further, you can use something like the XDI format, which adds to the columns, to the data itself. It adds some metadata, which can be very helpful actually in understanding what the data is. Now, the XDI format has been established more than a decade ago by Matt Newville in collaboration with Armando Sole from the SRF. Now, another plain text format that you might be familiar with is spec. This is the file format that came with the previous acquisition system that TSRF employed, which, as you can see here, it has the same logic as the XDI format. You have a lot of metadata at the top. You describe all the motors, you describe all the counters that you have in your experiment, and then for each of the scans that you acquire, you write the data in the same file. Now, there are many positive things that make text files something that we would want to keep to use in the future. So they are easy to read. Essentially, if you have a text editor, and nowadays there is one on any type of operating system you have, you can read them. You can also edit them rather easily. They will remain readable for the foreseeable future, and while we try to steer away our users from having their data analysis based on Excel and Origin type applications, like these spreadsheet-like programs, it's not always possible. So they are very happy when they can use these files, they can use them directly with them. There are some inconveniences. Some of them relate to the fact that the capabilities of storing more complex things in these text files is limited. So if you want to store images, you cannot. So there excludes them from being a one-for-all format. So you only can put inside some type of format data. And as they lack, and maybe an important point is that they lack compression support. So while you can compress data using another program or another software, this is not included by default in text files. Like some of these disadvantages, let's say maybe are not that important for a spectroscopist, but because the life of a facility evolves as a whole, so we have to take into account that other techniques have more stringent requirements in terms of the data that they need to store. we have to consider what the data format that is uniform in the entire facility, such that all the things we do downstream, like data preservation and data having a data catalog, it is simplified. So just to give you an example, but okay, you're probably all familiar with this. If you're trying to do, in the past, if you were trying to do fluorescence diffraction tomography, diffraction images, fluorescence data was stored in different type of files. The scan information was stored in spec, and the results of azimuthal integration was stored in yet a different format. So when ESRF decided to upgrade their acquisition system, at that point, there was also a group that decided on what should be the next file format that we will use to store the data. So at the time, HDF5 was the best candidate that checked all the boxes in terms of what we were expecting from such a data format. And this is taken directly from the HDF group website. So essentially, everything that we are interested in, it can do. We can have heterogeneous data. You can store a big amount of data, and you can also keep metadata with the data. This metadata that is so important to understand what we are actually having to describe the data itself. However, HDF5 is not perfect. HDF5 is a binary data format. So for someone that is used to just open a text file with whatever text editor it has on their computer, is not immediately obvious how you can actually extract the data from an HDF5 file. And even nowadays, as beamlines transition, spectroscopy beamlines transition from spec to BLIS, we get requests like this. This is actually a very recent one where a new beamline, which is a new beamline, a beamline that does XMCD mostly, and which is used to treating their data using these plain text files. They require that some of the data from the HDF5 format is converted to plain ASCII files, just so they continue to use their workflows. There are other things which I think they are more important related to HDF5 files. Data corruption can be extremely important concern, because being a binary format, if during the acquisition times another reader or someone else tries to open the file using reading mode, it is almost a guarantee that that file is going to be corrupted and the data is going to be lost forever. Of course, this is not the case with a simple format like a plain text file. If you really want to read more about why you shouldn't use HDF5, this is just a blog post that I found, which I found some very good arguments. But unfortunately for us, this is too late. The decision was taken. So what we need to do is to try to take advantage of what HDF5 has to offer, but also to circumvent some of these, let's say, some of these inconveniences that brings. So the first inconvenience is reading the data, and reading the data, actually nowadays more and more tools start to be to adapt themselves, let's say, to be able to read HDF5 data. This is the example of the LARIX from the large programs that is developed by Van Neuville. So this with the current version is actually, for me, is very easy. I just can use it to open an HDF5 file that was created at DSRF. Another example is PyMCA, which you also might know, which has had HDF5 support for more than 10 years now, before even the ESRF having HDF5 in-house. Just one thing that I would just to quickly highlight here is that in both cases, you as a user, you have to select what are the X and Y arrays, right? So you have to make a decision about what is the energy, for example, and what is the intensity among all the motors and all the detectors, all the detectors that you might have in the files. And this is going to become important later when I'm going to talk about NeXus. There are new tools that are developed to look at the HDFI files. Another tool also coming from the SRF is Silex View. This is part of the Silex toolkit, which is mostly geared at software developers if they want to build applications like graphical user interfaces, specifically for dealing with spectroscopy and other type of experiments. What Silex View adds on top is what maybe is difficult to see here. You have all these NX things that are attached to each of the groups. So Silex View is able to interpret the Nexus annotations and can take advantage of them. ESRF also invested recently some manpower in making the visualization of HDFI files even simpler. So you can actually now use your browser to look at these files. And this is an application that is hosted by the HDF group, but was developed at ESRF. So you go on this website, and you have the possibility of either selecting, drag and dropping, works very well, or opening a remote URL with an HDF file. For example, if I would go to the data portal at ESRF, I could select an HDFI file, point the URL to in this box, and then just have the data being displayed and being also able to look at the data and to plot the different things inside it. If you're a developer, so this is the latest level, you're probably familiar with the H5Py library. Is basically the de facto standard in trying to read HDFI files from Python. It has a very simple API, so it's very simple to use. It's very well documented on their website. And if one last thing, if you are really using an IDE like Visual Studio Code, which has become very popular recently, the same people that develop all these things at ESRF, they also developed a plugin. So now you're essentially in your IDE, you can easily open these files and plot whatever you're interested in and explore the raw data if you choose to do so. Okay, so now you see that reading HDFI files should not be the things that stop you from using them, because there are many tools that allow you to do this. And while HDFI files, so they bring some interesting features, there are, as I showed initially, there are some things that the user still needs to do in order to actually look at the data that is interesting. So you have to select which of the maybe tens of detectors that you have stored in this file, which one are interesting for you. So how can we think about solving this problem is by using NeXus. So NeXus is just HDFI files with added annotations. So essentially the tree-like structure that an HDFI file has is annotated with something which is something with annotation which are NeXus related. Now, I have to be honest, when I first looked at this and I tried to understand what exactly was happening, it wasn't obvious for me what was the added value in all this. Why would I want to do this? Why would I spend time in annotating the data using some definition decided by some people that I don't even know? So what I did next was just to so I created a file using an HDFI file using NeXus annotation and one that did not have NeXus annotation, and then I open it with some of this application that I presented before, and to see if something was different. So this is bringing me to the demo, that actually the part that I did during this metadata working group. So I'm going to switch windows, and you'll tell me if if you see my window. So
Yeah.
this,
Yep, it works.
yes. So this is for those of you who don't know, this is a notebook, a Python notebook, a Jupyter notebook. So where you have code, where the code is written in these cells, and every time I execute, I run a cell, the code inside it gets executed, right? So while it might be a little bit intimidating if you're not used to programming, I think the example is relatively simple to follow, so you don't get lost after a few of these cells. So here I just import some of the required packages. This is not really essential. And then I start by exploring one of these plain text files. So like an XDI file, I have this file on disk, and what I'm doing here is just looking at the 35 first lines of the file. So this is similar to what I showed you in the presentation. You have the metadata. So it's very easy to open this data and to look at it. Now I want to do some things, some changes to this data. First, I want to read it. So this reads the data from the file using NumPy functions. I do some transformation. I just divide what was called mutrans. I divided by I0, so by the monitor, and then I just plot the file. So this is a typical XF spectrum that you might expect. That I plotted, and I plot the data using tools that Python-based tools, right? Now, the next step is to do these two things. First, I'm going to create an HDFI file from this data, and then a second one, in a second step, I'm just going to create the same file, but adding NeXus annotations. Just going to guide you quickly through the code. Here I'm opening a new file. And I'm creating this hierarchical structure. I start by, under the file, I have a group that is called scan. In this scan group, I have a group that is called data. And in this data, I'm just going to insert these arrays, which are E, mutrans normalize, I0, and so on. So this can be done easily. And then this is just a representation of the tree-like structure of the data. With all the values here. Now, coming back to the fact that HDFI file is a binary file, so if I use the same command, which essentially should prints the contents of the file, you get a bunch of gibberish, right? So you clearly see that a text. This is what you would get if you'd open this file in a text editor, right? So you can distinguish some information, but it's clearly not made to be opened like this. Some of the tools, the web-based tools that I mentioned previously, can be used in these notebooks. So what I'm going to do here, I'm going to use this class to just open the file. I open the file. Even though this tool is aware of NeXus, because I don't have NeXus annotations in this file, it just doesn't give me, it gives me no visualization, so it gives me no information about the file. So I have to manually go in through the file and try to plot the data that I'm interested in. Okay, so you can do right. So I was able to get the text, sorry, the data from a file format like this text-based file format into an HDFI file. But having it in an HDFI file didn't really help a lot with like a usual task that I want to do, like get immediate access to what is the important data in all these in all these data sets. Okay, so this is where NeXus comes in, let's say, to save the day. Because here, what I'm going to do is I'm going to use the same skeleton as before. I'm going to create an HDFI file, but I'm going to add annotations. Now, the code gets a little bit more complicated. Let's say more complex probably is the good word. But but it's essentially not very different from what I did before. So again, I create a scan group, and then this is the part where the Nexus come into play. Is that I say that the default of this, the default of the file is scan1. What this means is that when I open the file, it knows that the data that by default should be used for some purpose is the one that is stored in scan1. And then I go one level further. So I say to create a data group in the scan1 group that I had before. And again, I add some attributes to this scan1 group, and I say that the default is this newly created data. I tell it what the signal is, what the axes are, and I can create even a title, which can be something useful, for example, for when it comes to plotting, as I'm going to show. Then here are the same commands. Sorry, now I realize that since I switched to another application, you don't see my pointer, but like here are the creation commands, and I can even add units if I choose to do so. All of these can be compressed into this representation where you have the same hierarchical structure you had before, but with this annotation on top of it. So, okay, I did some effort. I put some work. So what this does give me, when I open the file again using this viewer, because this viewer is Nexus aware, it automatically opened the plot that I wanted to display by default. So how it did that is, if I can look, I can inspect these NX attributes, and you see that for the file, the default is scan1. For scan1, the default is the data, and then you have everything that I added as information. You have it here. The axes are the energy, and the energy have units, which are EV. Okay, so the work that so all my work actually in the end it paid off, because I can, if I give this file to someone and it opens it with something that is Nexus aware, he will see the plot that I intend him to see. So it's just simply following a convention on both sides. Okay, if you are a programmer, you can also, of course, you can also take advantage of this of having the data Nexus formatted. Again, using this Silex library that I mentioned previously with this Silex view, but you also have tools to do input-output operations. So I open again this Nexus annotated file. I can just say data is equal to get the default from this file, and then I just plot the axis, the first axis, and the signal. And I can even recover the title that I gave. So now my plot, without actually knowing the internal structure of the file, I can, in a few lines of code, I can actually plot the data the way it was intended to be plotted. Now here are some links from, this is something that might be interesting, like some additional resources, like for example, how does the Nexus find what the default thing should be and how it change over time. So I'm not going to click on this. You'll have the notebook after the presentation if you're interested. So just to wrap this up, this is what Nexus give us. If we follow a convention on both sides, we will be able to take advantage of the actual, like, to simplify the life of the users. So with this brings me back to the next slides. So where we go from here, we are in the middle of trying to develop an application definition for XAS, where maybe in addition to having the energy and the intensity, the signal, to have some additional metadata that we require by default, such that the processing the processing of the data and the interpretation of the results are made easier. Here is an example of an application definition. This is for the small angle scattering data. they already have something in place. As of 2 or 3 weeks now, we started working on the NeXus application definition. So there is a repository where we already started to discuss some of the things. As you can imagine, sometimes we get stuck on some of the details about convention, nomenclature, and so on. I hope we're going to move past that, such that we will have an application definition that is going to be put in place rather quickly and is going to be usable very soon. So with this, just like to say thank you again for the invitation, and thank you for your attention, and I will be happy to take any questions that you might have.
Jan?
Yes, I just wanted to point out that there is an application definition. If you look in the manual, I linked it in the discussion. There is existing application for X-ray absorption spectroscopy. So maybe you need to start on that one and potentially modify that one if that doesn't satisfy your needs.
Yeah, that's well, that is exactly that was exactly the starting point of the discussion. But essentially, that application definition was developed. Actually, we don't know the history. I mean, we can trace back the history, but it was not developed with the community, without the input from the community. And it was very often, this was raised during the discussion, that some of the things that are existing in that definition do not really make sense, or do not cover all the use cases that we have. So of course, we are aware that that application definition exists.
Next is George.
Yeah, I I just noticed on slide 6, I think you showed 2 pictures where you would open NeXus files with PyMCA and Larix.
Yeah.
And it was interesting, those commands all look like spec commands, right? So can you explain why that is?
Yeah, I think the transition from spec to this new acquisition system that we have was already quite a hard pill to swallow for some of the users. So I think they wanted to keep some familiarity with what they used to have before. So those are underneath, they're all Python functions, which essentially just write a title following the same format as it used to be in the past. But there is nothing related to spec in these files other than maybe the similar name.
And then with opening, right? Because I know one nice thing, right? Like for instance, with PyMCA, if you open a spec file, you just have to open one file, right? And you'll see all those scans listed. Is that also how this was done? Is it a batch open, or do you have to go through and like open each HDF5 file one at a time?
So from what I use PyMCA, even in the past for spec, was always opening them one at a time. And then you have this drop-down menu that is also visible here, which essentially allows you to switch from one to the other if you want to open more than one file.
Right, right.
So,
if you want, but usually for an experiment, you get one spec file per experiment, right? So in
yeah.
HD5, I assume you get one HD5 file per scan. So
no,
then,
actually, we have one HD5 file for what we would be a sample. So it's very often that people structure the data like that. So they have a sample, and then they actually do. There is a new dataset command which essentially opens a new HDF5 file. So it's very often that people save everything that is related to that sample in one file. So
so you can hold multiple scans in one HDF5
yeah,
file.
sure.
Okay.
Sorry, I think I misunderstood you. Yeah, sure. That it would have been maybe more difficult to have one scan for HD5. Yeah, we have each scan is an NX entry, or like it's an entry in the HD5 file.
Right.
Thanks.
And just to expand on that, you can also put images in as well, right? So if you're doing something more complicated, you can have, you know, the you know, a 2D scan, several 2D scans, and then some images and, you know, different and alignment scans like all together. So that allows you to make more complicated groupings, if you will, of data.
Exactly. Yes.
Yeah.
Okay, next question is from Mark.
Hey, thanks for the talk. That was great. I was wondering about so in your example that you showed us in the Jupyter notebook, you were putting in the kind of NeXus type attributes or whatever that's called. You were putting them in yourself, and then later you were using Silex to kind of read them out. Does Silex also automate that process of like having to specify all of the attributes yourself, or are you still kind of stuck in that having to do all that manually?
Yeah, so there are some cases, like in the case for the NXData class, where it's the structure of this NXData is already, if you look at the NeXus documentation, is already known. So actually Silex just implements, so it knows what to expect when it finds an NXData class, and it just reads like the signal and the axis and so on and so forth. The things get a little bit more complicated when you go and you have an NX application, because while the NeXus gives you like the what it should, a NeXus application should contain, you have to do the Python implementation yourself. So now the things that we are doing for NXS is, once we have NXS class definition, we will create a Python implementation that is able to read data from that class. So yes, in principle, Silex has this possibility to read NX data. Silex does not have the capabilities to read like we have NX Tomo, for example. You cannot read data, NX data formatted in a different application. So you would have to implement in your code.
I'm asking about writing though. Like in
Writing.
my application, I'm thinking of saving our data, and my question is, do I have to do this myself, or is there
no,
a way to do
you
that
actually,
more
sorry, yeah, I misunderstood. Yeah, sorry. Yes, actually it has helper functions where you can specify easily what the signal is, what the axes are, but this again applies only for this NX data. Okay. I didn't use that in the presentation because you would have hidden a lot of the things that maybe make all this more understandable. So yeah, it has helper functions.
Yep. Okay, thanks.
Next question from Tejas. Tejas, you're muted.
Thanks. Hi, everyone. Thanks for the talk. I've got a question that's maybe a bit broader about defining new NX formats and what might be possible. So some of the new fluorescence detectors and applications, rather than storing simple 2D arrays of spectra, we want to maybe consider storing each photon, information about each photon as it's coming in. And therefore, the structure is a little bit, at least in my mind, harder to define, because you've got a variable number of photons per channel with metadata associated with each photon event. Do you think that this kind of data, we can define an NX style schema for this? Are you aware of any efforts like that?
Yeah, so yeah, this is a little bit something that I'm not used to, but I think already the fact that your data is, let's say, is not uniform, it might pose some issues, but again, I cannot speak with certainty about this. Might pose some issue even storing it at the HDF5 level, in the sense that either you would have to, I don't know, pad the things that are not there, or like, so it's essentially a way how you store these multidimensional arrays. Then going to NeXus, again, I don't know. We already having quite some struggles to converge on how to do things for 1D data. So I would say it's feasible, but I mean this whole thing is rather open to everything is open to discussion, right? So if you need something and if the community needs something, the NeXus format can be adapted to do that. But yeah, I cannot tell you anything for certainty. I'm sorry.
Okay, thanks. Looks like I caught Pete's attention anyway.
Okay, next question is from Rima.
Hi, thank you for giving the talk. Actually, on the point just made from Tejas, so there is a mailing list that he may want to send his question to. There has been some discussion in the NeXus committee recently about storing different channels and you know, whether we should allow text labeling of arrays and things like. Anyway, that's inside baseball. The and to Jan's point, yeah, Matt Newville actually spoke to the committee last year to express some problems with the original XAS format that was there, and I think that's when this process that you presumably are describing now started, wasn't it? To get the community really engaged in.
Precisely.
So it's great to see there's progress on that. But of course, one of the reasons I'm writing is I posted in the chat a link to NextPy, which I hope people should be made aware of. So NextPy is another application which is specifically for reading NeXus files. It can read other HDF files away as well. So it has a GUI, but actually perhaps more relevant to the question that, for instance, Mark raised, is that there's another API called the NeXus Format API, which I think in the past Armando has said ESRF has recommended to user scientists, if not to developers. But the NeXus Format API simplifies the reading and writing of NeXus files by writing a lot of higher level routines that automatically write the attributes that we're talking about. So, you know, you don't have to worry about having to write an NX_class attribute for the group classes. Defaults are handled. NX data in particular, of course, it'll handle the whole arcane ways of defining what are the signal and what are the axes, which you alluded to. So I'd encourage you to and other people to check that out if you really want to have a simpler way of writing NeXus files. So just thought I'd mention that. Well, thanks for the talk.
Yeah, thank you for the question. I feel I'm not in the best position to give this talk, seeing that you're attending. So it's like
no, not at all. No, I was delighted that, I mean, the ESRF is actually, for a while they were a little bit resistant to using NeXus, but actually they've been some of the most constructive people in the whole NeXus community. So I'm really delighted by talks like yours. Thank you.
Yeah, thank you, and sorry for the omitting, of course, NextPy for visualization and all the details that you mentioned. What I'm not sure that the NeXus format is actually extensively used in terms of reading and writing NeXus formatted files. So that I will also have to see with Armando. But the Silex implementations for sure doesn't use that.
Actually, perhaps I could quickly mention one of the goals of the NeXus format was to make it easier for scientists to use NeXus, because I think as developers, NeXus is getting increasing traction at facilities, but I think it's not so widely used by the scientists who get the data, and that's, I think, because of the lack of intuitive tools for them to use. And so we're hoping to change that, and I hope that people can, you know, look into that and comment if they think there are other things needed doing.
Okay,
Thank you.
Thanks.
Okay, question from Mark again.
Right. So we're in the process of moving a lot of our controls over to Blue Sky, and I saw that APS Tools has some support for writing NeXus files. So I'll probably start there. But my question then is that something you have any experience with? Are there other things I should look at that will make that easier, or perhaps it's just not something ESRF even is interested in, but I figured I'd bring it up in case you have any thoughts.
So what I can tell you is the way some of the other techniques are dealing, which are a little bit maybe more advanced in this respect. Like in the case of tomography, the way it happens right now at the SRF, because there is a lot of heterogeneity in the data, we have a tool that digests data from different places, and then it actually converts that data into a NeXus format. And this tool actually relies on an implementation of the NX Tomo application definition, which is it's a Python tool that was also developed at the SRF, which is capable of writing the data in a format, or like following the NX Tomo application definition. So I don't know. Again, I don't know if it really answers your question, but this is how we are essentially doing it now. We're just implementing. We have a Python tool that is able to write data in a following certain NeXus convention for a certain application definition.
Okay, thanks.
Question from Peter.
Hi there. Thanks very much for your presentation. I appreciate that you have made such a good understanding of the NeXus project. I think that's fabulous. The tools that you have for writing NeXus files at the beamline, are those specific to the beamline, or is there a general package of library support that any beamline could use?
Again, I'm going back to this example of the tomography beamlines. There is a single package that is being used for all of them to write data in following the NX Tomo class definition. Of course, once we have an NXus class definition, we will probably follow the same path, meaning that we will develop something like a simple Python package that is able to take data from different beamlines and write it into the NXus, following the NXus definition.
Okay, thanks.
Yeah, my pleasure. It's very interesting because I see a lot of people which are in the NIAC, which I never met. I'm giving a presentation about NeXus and I feel a bit overwhelmed. But
Well, you attracted our attention for sure.
yes, exactly.
I'm thinking along the lines of a template sort of idea for implementing the various application definitions for writing data, that possibly having a template may be of more general use.
Sure.
Okay. Because writing data to an application definition, in my experience, involves some expertise that's not obvious to start with.
Yes, but we don't expect scientists to do this. So we're
Okay, any more questions? I think no more. Okay, we can continue discuss in our chat. If you have any information, any transfer, I can direct transfer to Maria's, or you can find Maria's email in ESRF website easily. Okay, today's SIG meeting is here. Thank you, everyone. Thank you, Maria. It's so
Thank you.
attractive talk.
Yeah.
Thank you for
Thank
your
you.
invitation again.
Thank you. It's great.